Hi class! Today we are going to be covering exponential functions. But before we get into exponential functions, I want to review real quick the two types of functions that we covered last chapter. One of them was polynomial functions, and one of them was rational functions. And as you can see, both polynomial functions and rational functions have exponents in them. In fact, what makes these different from the exponential functions of this chapter? Well, that's a good question. So before I answer that question, I do have three functions that we have. F of x is a polynomial, g of x is a rational. And what kind of function do you think h of x is? Is that a polynomial or is it a rational function? It looks like a rational, doesn't it? It has a fraction line and it has something in the denominator. However, would you be surprised if I told you that that actually is a polynomial function? Yes, h of x is a polynomial function because when you look at it, there is no x in the denominator. I could rewrite it to look like this. And you can see that it just becomes x squared plus, well, it becomes 3 over 2 x squared plus 7 over 2. And those fractions are just the coefficients, but they are, but there's no x in the denominator versus the rational function g of x. So what made h of x a polynomial? It was the location of the variable, that all of the variables were in the numerator and there were no variables in the denominator. So that's going to be a clue to what makes this different from an exponential function. With k of x, we see that we have 5 to the power of x plus 7. Let me highlight a few of these variables in here. Notice that for all of the x's in f, g, and h, all of those were the base of the exponents. We had x to the 5th, x to the 4th, x squared. But in k of x, the x is actually the exponent itself. We have 5 to the power of x. And it's the location of the variable that determines that k of x is an exponential function, while the others have exponents, but they are not exponential functions. With that in mind, we see that an exponential function is a function in the form of c a to the x. And the a is the base of my exponent, the x is the exponent itself, and the c is the coefficient. We have rules about the a and the c. So we have this function with a coefficient of c, and the a is the base of the function, the x is the exponent. We have three functions here. For g of x, my constant is 5, 7 is the base of the exponent, and x is the power. Now remember that if we're going to plug a value in, you want to do the exponents before the multiplication. So we would do 7 times 7 times 7, and then you multiply that answer by 5 afterwards. You would not want to multiply the 5 by the 7 first before you take the power. With h of x, we have a -3 as our coefficient, and we have the base is a 5, and then the variable is x. And then we have k of x, where my coefficient here is 1, and the base of the exponent is 3. So we didn't bother writing the 1. I want to remind you that when you're looking at the domain, you're looking at rules for the variable. So we're looking at what values x can be. And in this case, x can be all real numbers. But we also have rules for the a, which we didn't typically have before, but we have to be very careful about the a now. A has to be positive and it cannot be 1. We'd write those this way. A is greater than 0 and a is not equal to 1. Let's take a look at some equations and see if we can come up with a better concept of what these exponential functions are. For our first question, we're given f of x is 2 to the x. This is where my c value is 1, my a value is 2, and x is my variable. And you have g of x, where my c value is 3, and the a value is 2. Looking at f of x first, I plugged in the values that we have here, and let's just simplify it together. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 squared is 4. 2 to the power of 3 is 8. Then we have negative powers, and negative powers turn things into fractions, but they're positive fractions. So 2 to the power of negative 1 becomes 1 over 2. 2 to the power of negative 2 becomes 1 over 2 squared, which is 1 over 4. And 2 to the power of negative 3 is 1 over 2 to the third, which becomes 1/8. Filling in our g function, we find that 3 times 2 to the power of 0 is the same thing as 3 times 1, so we get 3. 3 times 2 to the power of 1, we get 3 times 2, which is 6. 3 times 2 to the power of 2 is 3 times 4, which is 12. And then 3 times 2 to the third is 3 times 8, which is 24. Notice that I'm doing the 2 to the powers first before I multiply by the 3. 3 times 2 to the power of negative 1 is 3 over 2 to the power of 1. 3 times 2 to the negative 2 power is 3 over 2 to the power of 2, which is 4. And 3 times 2 to the negative 3 power is 3 over 2 to the third power, which is 8. You have to be careful if you're multiplying by a coefficient that you always do the multiplication after you do the exponent. For the theorem at the bottom of our page, we see that the ratio of any two numbers on our list is going to be the same as the base of our exponent. That means if I compare any two numbers, they're all going to be off by a factor of that base. In this case, the base of our exponent was 2. So any two numbers that we see will be related to each other by a ratio of 2. For example, looking at g of 2 and g of 3, we see that 24 and 12 are our answers, and that if I said 24 divided by 12, we would get 2. That also means that if I know g of 2 is 12, to find g of 3, all I have to do is take my previous answer and multiply it by 2. I don't necessarily need to plug it into the whole function and figure it out. If I know one of them, I know the number right after. So if I know 12, then I know that right after it, my answer is going to be 24. We can use that theorem to determine if the given functions in these graphs are linear, exponential, or neither. So what we're going to try to do is look at the gaps between our y values and see if that gap is constant, then it's going to be a linear function. And if the gap is not constant, but the gap has a ratio that is constant, then it will be an exponential. So let's go ahead and see what type of gaps we can come up with. For g of x, we see that the gap between 2 and 5, we add 3 between them, we add 3 between 5 and 8, you add 3 between 8 and 11, you add 3 between 11 and 14. Because that gap was constant, then this function is linear. Let's look at f of x, capital F of x. This gap, oh, those are a lot of fractions. And I just know that those gaps are not consistent. But let's see, what did I multiply by to get this? And notice to get from 1 to 3 over 2, you probably multiplied by 3 over 2. And to get from that to the next one, we probably multiplied by 3 over 2 again. And it looks like between the next ones, it will be multiplied by 3 or 2. Let's look from 2/3 to 1. If you take 2/3 and you multiply it by 3 over 2, then that becomes 1. And so that, the gap is not a plus 3, it's not an additive constant, it's a multiplicative constant. We're always multiplying by the same thing. So this one is an exponential function because you can see that you multiplied by the same number each time, versus the first one, which was linear, because you could see we added the same number each time. For f of x is 3 to the power of x. What is f of 4? Well, we just take f of 4, and we would say that's 3 to the power of 4, which is 81. So our point is 481. For part B, we're saying that f of x is 1 over 9. So we're going to replace the f of x with 1 over 9. I'm going to get 1 over 9 is equal to 3 to the power of x. So now their question is, what is x? So notice before they said plug 4 in for x, then say what is f of 4. This question now says our y value is 1 over 9. What x value gives me that? And that's the same thing as 1 over 3 squared. So our x in this case would be -2. And so the point on the graph would be -2, 1/9. When we look at the graph of f of x is 2 to the power of x, that is a function that we've already evaluated today. So I'm just going to refer to those values when filling this in. We've got 0, 1. We got the point 1, 2, the point 2, 4, the point -1, 1/2, and -2, 1/4. And so I'm just going to connect these and do my best. And my value never becomes 0 and it never goes negative. So this is the graph. You want to act like there's an asymptote there. So remember, asymptotes are lines that we never cross when they're horizontal, when they're going towards the infinity. When we look at the graph of G of x, we notice that all the values are similar to the ones we just graphed, but they're in reverse. We get 1/2 to the power of 0 is 1. 1/2 to the power of 1 is 1/2. 1/2 to the power of 2 is 1/4. 1/2 to the power of -1 is +2. And 1/2 to the power of -2 is +4. So when we graph that out, it's a very similar graph to the first graph. It has a lot of the same properties. It still has an asymptote at y equals 0. It still has that same basic shape, but it's just in reverse order. It's almost like you flip it on the y-axis, and you do. Because 2 and 1/2 are related, they're just separated by a power of -1. We can plug in any number for our exponent, so our domains are always going to be all real numbers. And for these basic graphs, we can see that the range of values is always going to be positive. So we're going to go from 0 to infinity, and we're not going to include 0 because we can never get 0 as a result. So I'm going to put a parentheses there. We don't have any x-intercepts. And we do have one y-intercept. And if our c is 1, the coefficient in front of our exponent is 1, then our y-intercept happens at 0, 1. This point was shared by both graphs. We have a horizontal asymptote. Its equation is y is equal to 0. And this property, all of these properties that I wrote down are shared by both of these. Both the 2 to the x and the 1/2 to the x. All of them are smooth and continuous. The only difference is that one is going up and one is going down. When is it increasing? Well, for the graph where my a value was greater than 1, then it was increasing. But for my a that was less than 1, but keep in mind it still has to be positive, then it was decreasing. And so that's really the only difference between these two graphs. If you have a fraction that's less than 1, and you're taking it to a power, then you're going to have a decreasing function, because each time you multiply by that fraction, you're going to get a smaller number. But if you have a number for your base that is greater than 1, then each time you multiply it by it, it's going to get greater, so it's going to increase. Question number 5 asks us to use transformations to graph f of x is 2 to the power of x plus 2. I just want to ask you, if we're going to do transformations. We want to check out if the plus 2 is happening inside our function or outside of our function. Meaning, is it happening to our x or is it happening after we apply x? And this one I would say is inside our function. So it's going to be manipulating our x. And always when we do the manipulations for x, it's going to do a horizontal change. And so since it says x plus 2, we know we're going to shift it. And all of our shifts for inside our function always go the opposite direction. So that means that this graph is going to shift to the left 2 spaces. You can see that all of those points move left 2 spaces. Let's watch it move. So I put a third function on the side. It says 2 to the power of x plus h, and then outside of the power I have plus k. Keep in mind that the plus h is inside my function. It's modifying my x, so that's going to do a horizontal shift. The plus k is outside of my function, so that's going to modify the y value. Let's first see the h value. I'm going to move this first from 0 to 2. You're going to see our graph go from the original parent graph, and it's going to shift left 2 spaces. And notice that, see how it's shifting left 2 spaces? And I can change this, and you can see that when I'm shifting to negative values, it goes to the right. When I go to positive values, it goes to the left. And then you can also change the height of each part by changing my k. And when k goes positive, it's going to go up. And when k goes negative, it's going to go down. So remember how h and k modify functions. H is always going to be the opposite direction horizontally, and k is going to be the same direction vertically. Now, e is a special number in exponential equations. Some people call it the exponential number, some people call it Euler's number. Let me write that for you. His name is pronounced Euler, and it's spelled with an E, so that's where we get the little e from. But it also has other names, and the other has plenty of definitions. One of the definitions is in your textbook. But I want to say that that definition is a little bit useless for us right now. We're not going to be doing anything with that, other than the fact that you should know that E is approximately equal to 2.718. And if I were to continue that decimal, it would go on forever and ever. It's an irrational number, similar to pi or radical 2 or any of those other numbers that we use some type of notation to symbolize, because we can't write 2.718 and continue on forever and ever. So we're just going to assume that that's the value, or we're going to take on that value every time we think about e. And we're going to treat it just like a constant, like it is. And you can have functions that have e as the base of your exponent. Let's look at the graph of e to the x. I have that function written in blue on the left-hand side and graphed in blue. And you can see that you have the point 1 and 2.718 as one of our points. We also have the point 0,1, and as most of our exponential functions have on our graph. And so this is our parent function with the exponential e as our base. And the question in our homework says, use transformations to graph e to the x minus 1. And notice that that minus 1 is outside of the e to the x function. So that's going to be a vertical shift, and that's going to shift everything down 1. Let's compare the graphs. So you see the green graph takes all of the blue points and shifts them all down 1. We want to determine the domain, the range, and the horizontal asymptote of the function. So let's go back to our other paper. Before we look at the domain, range, and horizontal asymptote of e to the x minus 1, let's look at the domain, range, and horizontal asymptote of the parent function. Just like all of our other graphs, my domain is all real numbers, my range is all positive numbers, and my horizontal asymptote is at y is equal to 0. What happens when we graph e to the x minus 1? Well, we said everything shifts down 1. So everything, all the y values are going to be shifted down 1. Our horizontal asymptote is going to be shifted down 1, and our range is also going to be shifted down 1. Now our domain deals with x values and nothing changes to our x values, so our domain is going to remain the same, but the range is going to change a little bit. And our range is going to subtract 1 from both numbers, so 0 minus 1 is minus 1, infinity minus 1 is still infinity. And then for my horizontal asymptote, that is also going to be, the y value is going to subtract 1, so we're going to put my horizontal asymptote at y is equal to -1. Now, we talked in the beginning how exponential equations are one-to-one functions. Therefore, they follow special rules, which is if their outputs are the same, then their inputs must be the same too. So if a to the u is equal to a to the v, and those outputs of each exponential expression is the same, then the exponent must be the same as well. So then we would know that u must be equal to v. This is not by dividing anything, this is just by taking some concept of one-to-one and applying it to this. But we're going to use that to help us solve each equation. One thing to notice about that rule is that the a has to be the same for both expressions in the equation. And so we want to have the base of the exponents the same. So for this first question, we do have to rewrite it a little bit. We want both of the bases to look like 5. So we're going to write the right-hand side as 5 to a power. And this one would be 5 to the power of -1. Because now we have this statement made, x plus 3 is equal to 1, or to -1. And so we're going to say x plus 3 is equal to -1. And then subtracting 3 from both sides gives us x is equal to -4. For the next question, you have to be familiar with your exponent rules to be able to solve it correctly. So it asks you e to the power of 4, the whole thing to the power of x, and that's multiplied by e to the power of x squared, and that's going to be e to the 12th. Notice that on the left-hand side, I have e to a power times e to a power. We're going to apply the exponent rules. The first one is e to the power of 4x and e to the power of x squared. We just simplified the 4x first. But when I have something like this, and they have the same base, we're going to add their exponents. So that becomes e to the power of 4x plus x squared is equal to e to the power of 12. So we get 4x plus x squared is equal to 12. And we're going to pull that out. And then solve. So there's our solutions. We have -6 and 2. Because we have two solutions, we must put it in set notation. And there's our two solutions. Our last example has two exponents equal to each other, but they do not have the same base. But I can rewrite them to have the same base. In this case, the base would be 2. So I'm going to write 4 as 2 squared. And then the other side is 2 to the power of x. And what we do with this is we multiply the 2 times the x squared. So I would get 2 to the power of 2x squared and 2 to the power of x. Once again, making sure that you have an exponent equal to an exponent, we're just going to take those exponents and set them equal to each other. And then we're going to solve. Be careful when solving something like this because it's easy to think that you want to divide both sides by x, but you can't do that because you don't know what the value of x is, and you don't know what's going to happen if you divide both sides by x. So it's better to move it over to the same side and factor and solve that way. Once again, I have two solutions. So I'm going to write them in set notation. And there you go. There's your solutions. Make sure that when you're solving exponential equations that you're always making sure they have the same base, and that you're following the rules of exponents to simplify it until you have one exponent equal to another exponent, and that way you can make sure that you get your answer. Make sure that you simplify that first. You shouldn't try to change it into an equation at this step. You should wait until you're at this step and say, okay, you know what? Now I can take just the exponents and make an equation like this that's easy to solve. Alright, get to practicing, and if you have any questions, let me know. Thank you and have a good day.